This apparatus is a heat transfer service unit used for performing the various experiments based on various phenomena in a heat transfer. So this unit serves as a supply unit as well as the instrumentation unit for various types of heat transfer experiment. If you this supply unit consists of the supply of laboratory water. This is the controlling for input of the laboratory water, and this will be act as a outlet for laboratory water. So these are the water connections if required in various heat transfer experiments. Then it consists of instrumentation. This is DTI, the digital temperature indicator, which indicates up to 8 number of temperature sensors. The reading of temperature sensors will be displayed here. This will tell you the input supply voltage. This will tell you the current taken by the various accessories. And with the help of this variac, we can change the input to the various experiments up to a desired value. These are the switch for the mains. This is the switch for the heater, and the heater input is here. The heater connection will be connected here, and these are the connectors for various temperature sensors used in your system. So these heat transfer experiments can be used as a supply source for the water connections, can be used as a heat input source, and also used for the instrumentation to detect the various values of the temperature sensors involved in the experiment. So here we will use it for 4 types of heat transfer experiments. The first experiment we will describe here is linear heat conduction, that how the heat conducts linearly across the metals, different metals. For linear heat conduction, here our aim is to find out the thermal conductivity of various metal rods like copper, stainless steel and aluminium. As you can see, this is the heater source. Here heater is connected. A cartridge type of heater is connected at the one end, and this will be connected to the heater source like here. The other end is connected to the laboratory water like this. So this will be connected with the help of adapters here. So one end is cooled with the help of the supply water, and other end is heated, and then we will see the temperatures at different positions of this metal rod. This part is of brass, this part is also of brass, and this can be removed as per our requirement. So we will lose this. You can see we will lose this, and this will come out like this. So this is the metal brass, this is also brass, and this is also brass. So if we connect it here, it will form a single unit. And these are the various connectors with the numbering. So we will connect all these connectors to these temperature sensors, and the temperature will be displayed here. Then we can give the input as per our requirement with the help of this variac, and what is the voltage and the current taken by the instrument will be indicated here. So with the help of this voltage and current, we can find out the power input to the heater. Here we can give the laboratory water at the other end, and with the help of measuring beaker you can find out the flow rate, at how much flow rate your laboratory water is input at other end. So one end is one end is cooled with the help of laboratory water, and one end is heated, and now the heat will go towards the lower potential. As we know, the heat always goes towards the lower potential. So heat generate from here and will go towards the other end, towards the colder end, and we will wait for the steady state. After some times, when the values of the temperature sensors are not changing, then we can assume that our steady state is assumed. Then we have to note down all the 8 temperatures with the help of this temperature indicator, and we have to formulate into the formula and find out the thermal conductivity of the metal used. As you can so your all the 8 temperature sensors will be here. However, while calculating the thermal conductivity, you have to use these 4th and 5th temperature sensors only. These are the indicative temperature sensors that tell you about how the heat is going from this end to this end. But when you are calculating the thermal conductivity for suppose copper or stainless steel or brass or aluminium, you have to take in consideration only the sensor number 4 and the 5. Okay, so to switch on the apparatus, this is the main switch. As you see, this is the main switch. So this is indicating the temperature. This is showing the open because there is nothing connected to this connector. So when I go to the first temperature sensor, you can see that it is showing the temperature sensor at the first point, 25.2. If I connect it similarly the second one, and with the help of this scrolling buttons, you can scroll between the different channels. From this, you can first, this is channel number 2. It also starts showing. When goes to channel number 3, this will show as open because nothing is connected here. So I can connect the temperature number sensor number 3 also. So in this way, I can connect all the 8 temperature sensors and can find out what is happening when I give the heat input to this heater. I can give heat input by wearing this. So before that, you have to switch on the heater. When you switch on the heater, you can see I can give the heat input, and the heat input what I have given to the heater will be visible with the help of this voltage and the current. So when you connect your laboratory mains water connection to here, you can see also the flow rate with the help of measuring tank. So in this way, you get all the things. You have the temperature sensors, 8 temperature sensors, you have the heat input, you have the cold water input. So in this way, you can find out the different thermal conductivities in case of, and also demonstrate the students about the linear heat conduction, how the heat conducts linearly. Now, after that, we will go to the second experiment, that is radial heat conduction, how the heat conducts radially. Setup for radial heat conduction. In radial heat conduction, we have used a plate, test plate. The material of the test plate is a brass, which is 6 mm in thickness and 104 mm in diameter. At the center of this plate is installed a heater which heats this plate, and the heat is going radially outwards, and the outer end of the plate is connected to the cold water connection. So similarly as in the radial heat conduction, one end is heated and the other end is cooled. In the similar way, this plate is heated from the center, and the outer edges of this plate and in the diameter area is cooled by having a cold water connection at the outside of this plate. So similarly, we have the sensors installed at various positions, so we can find out how the heat is going radially outwards, and these temperature sensors are connected to the temperature connectors of the heat service unit, and the heater is connected to the heat input. Similarly, we can give the heat input with the help of this variac, and we can know how the different temperature sensors are changing on this DTI temperature sensors. So when you install this experiment, you have to fix it with the help of these 4 knobs given at the 4 ends. After fixing the experiment and connected the connection to the fixing the connections to the laboratory input, you can switch on the mains, wait for the meters to get stabilized, and then you have to switch on the heater, and with the help of scrolling buttons, you can see how the temperatures is changing at various input. So to have the power input, we have to multiply this voltage with the current into the power factor. If you know, generally we take the power factor as 0.8 or 0.9. Okay, so first of all, you have to give some heater input, wait for then you have to connect a laboratory mains, and then you have to wait for the steady state. Steady state means when the temperatures are not changing no more, or if there is negligible change in temperature over a significant period of the time. So when the experiment is over, you have to switch on the separators, remove the knobs and the heat input, and your instrument is ready for the next assessment. This is the accessory for find out the heat transfer coefficient in case of an extended surface area. So here extended surface area, to show the extended surface area we have used a rod that is extended from a piece of a rod. A rod is extended from a piece of another rod having a larger diameter, and this rod has a shorter diameter, or the rod dia is 10 mm. The material used here is copper, and the length of this rod, extended length of this rod is 297 mm, having 7 temperature sensors installed on the outer surface of this rod, having 48 mm apart. Okay. So as you know, in this apparatus we will give only the heat input at one end and see how the heat extended to the farther end of the rod, and then we will find out the heat transfer coefficient. Again, we will use the instrumentation provided here, heat transfer service unit. We have temperature sensors. So all the 7 temperature sensors will be connected to these connectors. Heat input will be connected to the heat input source. Then we will switch on the mains. We can see all the temperatures, how the temperatures are changing here, and we can give the heat input according to the requirement. Also, you have to note that whenever you are giving the heat input, you have to refer the manual at how much maximum heat input or maximum temperature limitations given for that particular accessory, and you have to take care not to exceed that limit so that the filters cannot be damaged. As you can see, we have used heaters of different capacities, and each heater has a limited capacity. So we have to go over that value, and that values we can find out in the instruction manual. Another accessory, another heat transfer experiment used with this heat transfer service unit. The name of this unit is thermal conductivity of liquid and gases, and as the name indicates, this accessory is used to find out the thermal conductivity of various liquids and gases. Now if we talk about the arrangement in this experiment, it consists of a rod, cylindrical rod having diameter 39.6 mm, and a heater rod is inserted into the middle of this heating rod. So this heating rod will act as a heating source. Above this heating cylinder of 39.6 mm, there is another cylinder which has the ID of 40 mm. So you can see the inner cylinder has a OD of 39.6 mm, and the outer cylinder has an ID of 40 mm. So there is an annular gap of 0.4 mm is maintained with the help of O-rings installed at the outer edge of the heating rod. So in that annular gap, we can fill different types of liquids and gases, and with the help of various temperature sensors installed in the heater and at the outer periphery of the outer cylinder, we can find out the thermal conductivity by the temperatures changing. So if you can see here, we have given the different arrangements for introducing the liquid or the gases into the periphery. This is the arrangement used to insert. If you want to insert the air, you have to use this syringe, or you can blow out the air by keeping this valve open, and then you have to inject it and then close it, and you have to make sure that this also is closed. So I can assume that air is blocked into the periphery having a 0.4 mm annular gap. So first of all, if you want to find out the thermal conductivity of that liquid, you have to first calculate the thermal conductivity of the air to find out what is the actual heat input to that gap. So for that, what we will do is, first of all, we will perform the experiment to find out the thermal conductivity of the liquid and use those calibrated values to find out the thermal conductivity of liquids such as water or oil or other viscous fluids. So same for introducing the liquid, you have to connect this to this point. Sorry, you have to connect this here to this point, and the liquid will be comes out here, and you can see the air, all the air bubbles are coming about, and when more air bubbles are coming out, you have to close this valve, you have to close this valve also, and now you can assume that liquid is present into the another gap. Then you have to switch on the heater, as earlier we had this, we did heat input here, switch on the heater, give some heat input and see how the temperatures are changing here. So at the outer periphery there are fins cutted, and in both between those fins cooling water is running down. So it is taking the heat from the heater to the liquid, and from the liquid it is taking the heat out. So if we know what is the temperature or temperature of the heater or heat input, and we know how much heat input is getting out and how much heat input is getting in, so by taking those temperature differences we can reduce the thermal conductivity of various liquids and the gases. For more further details, the inner diagram or cut sectional view of this apparatus is already given in the instruction manual.